This lesson is for Unit 1, Section 1, Day 1. It's going to cover some topics that are in Sections 1, 2, and 5 from Chapter 1 in our textbook. Some terminology we're going to go over, which you may already know or not: point, line, line segment, plane, angle, congruence, bisect, parallel, and perpendicular. So let's start by getting into some of these terms. A point is any location in space. A line is a set of points that extend infinitely in both directions. So a point would be just a dot, right? And it's usually labeled. A line is going to go forever in two different directions. A line segment is kind of like a line, except it stops. So if we did not have arrows on this and instead had points on the ends, that would be considered a line segment. A plane is any flat surface that extends infinitely. We usually draw them as a four-sided figure when we're just drawing a plane, but really if we're talking three-dimensional figures, that's really where planes start to come into play. An angle is two adjacent rays with a common endpoint, and we call that endpoint the vertex. Congruence, or when any geometric figures have the exact same size and shape. So we can have segments be congruent, we can have angles be congruent, we could have squares be congruent. Any kind of geometric figure can be congruent to another geometric figure. The term bisect, if we know the word bi means two, it means it's split into two congruent pieces. So a segment can be bisected if we split it into two congruent segments. An angle can be bisected, and so on. Parallel is when two geometric objects never intersect. If I'm specifically talking about lines, I'm talking about coplanar lines, or lines on the same plane that never intersect, but planes can be parallel as well. And then perpendicular is when two geometric objects intersect at a right angle. So how we're going to name our geometric objects. If I have a line, I could either name it as line PQ. Oh, it's not going to work like that. Let's try this. Line PQ, where I do the two letters, and then a line with arrows on both sides above it. But you'll also notice sometimes we have a little letter, in which case I'd write the word line, and then the script letter. So sometimes I use my script like that, line L. A segment, I would put the two endpoints, and then I'm going to use just a bar above it, right? There's no arrows on this, so there's no arrows on my bar. A ray, now that's not a term we talked about, but a ray is kind of a mix between a line and a segment. It starts at one point and goes forever in one direction. So we generally start with the point that doesn't have the arrow, and then we draw the one arrowed line above it. For an angle, we're going to name it either by three letters with the vertex in the middle. So the vertex is the place where the two sides meet. So I can call this angle. I'm going to use an angle like this just so I don't get confused with L's. Angle E is, actually that's that way, one letter. Three letters would be E in the middle, and then a letter from each side, D and F. And it doesn't matter what order D and F are in. I could actually have called this angle FED as well. And sometimes we're going to have a number inside the angle like this. And I know it's not representing degrees, it's measure, because there's no degree symbol. So I could also call this angle 1. When numbers are available, I would definitely choose to use them. If numbers are not available, you have to use three letters if there's more than one angle at that vertex. If it is on its own, like this particular picture, we would be able to use just the one letter. All right. So naming a plane is either by 3 of the points that are not collinear, which means I can't draw one single line between all 3. So I could call this plane BCD because those are 3 points not in a line. Or I could call it plane K. Notice there's no dot by the K like there was by the B, C, and D. So I can call it plane K. And again, that's supposed to be more of a cursive K. Some things we should know about our points, lines, and planes. So any 2 points will make a line, which also means that a line must contain at least 2 points. When 2 lines intersect, they intersect always at one single point. Any 3 points that are not collinear can make a plane, which then also means that a plane must contain at least 3 non-collinear points. If 2 points lie in a plane, then the line containing them lies in the plane. So as long as points D and E are contained in R, line DE is contained in R. And then when 2 planes intersect, their intersection is a line. So we're going to start here. We're just going to draw and label a figure for the relationship that's described. So they're giving us a lot of information. We have plane R, so I already know I'm going to have a nice big shape. I'm going to fit everything, and it's going to be called R. It contains lines AB, line CD, and line EF, but there's a little more information before I go further. Line AB is parallel to line CD, so I could actually do that right now. If I'm going to draw 2 lines that are parallel, I'm going to draw with the best of my ability to make them look like they're never going to touch, and I'm going to label them with A, B for one line. I'm going to put points on them and put my letters. C and D for the other line. And now they also tell me that CD is perpendicular to EF. Right? So this symbol meant parallel. This symbol means perpendicular. So I know that it's going to intersect line CD at a right angle. So the symbol for a right angle is a box. I'm going to make sure I put the points E and F on this. That's my dog. She's saying hi. I could have drawn the line to extend here, and it wouldn't make a difference. That would still be perpendicular to CD. It could be intersecting AB. That's fine. It just didn't tell us we had to draw it like that, so we're not going to. All right, so you're going to go ahead and answer this question as best you can in the program. All right. For this one, we're going to give another name for angle 1, and then we're going to state the vertex and sides. So I see that angle 1 is here. Angle 1 is in this corner, so its vertex is X. Its sides would then be XU and XY. And another name for it, I can't call it X because notice there's another angle here, there's another angle here, there's another angle here. So I'm going to have to name it by the 3 letters. So I'm going to call it angle UXY. Okay? So you're going to go ahead and try to answer this problem in the program. All right, congruent segments. We already talked about congruence as geometric figures being exactly the same. So if 2 segments have the same measure, they are congruent to each other. They're mentioning red slashes here, really any color slashes. I call them dashes sometimes. So 1 dash or 1 slash matches with 1 slash, those are congruent. Just something to note here in terms of terminology and the way we write things. Without the bars, we're really talking about the measures, like the actual 1.7 centimeters. With the bars, we're talking about the segments themselves. So measures can be equal, numbers can be equal, the segments have to be congruent. So we cannot switch between the two. The equal sign has to go without the bars, and the congruent sign has to go with the bars. So think about it. If there's something over it, there's something over it, right? If there's something over the letters, there's something over the equal sign. So I'm going to list the segments that are congruent to AH. So AH is right here, and it has 2 dashes on it. So any other segment that has 2 dashes is also congruent to AH. So I notice that HG has 2 dashes. I notice that GF has 2 dashes. And that FE has 2 dashes. So go ahead. There are 2 different sets of congruent segments in this picture. Name the ones that are congruent to each other. Okay, congruent angles, again, are angles with the same measure. So we notice that this one has 65 degrees, this one has 65 degrees, and if you notice there's a curved line in each of them. There's one curved line here, one curved line here, that shows that they're congruent to each other. When it gets 2 curves, that means it's congruent to a different angle. So this angle and this angle are not congruent, they don't have the same number of curves, right? And that's how we show congruence for angles. So in this example, we're going to find the measures of the angles they're asking for using the protractor, and we're going to identify which ones are congruent and mark them in the diagram. So YOW. First, let's just talk about the protractor. We notice that it has 2 different sets of numbers. It starts at 0 on the outside and goes to 180. When if I went on the inside, it starts at 0 on the right-hand side and goes to 180 on the left. Just be consistent in whatever you're using. So right now I'm actually going to stick to just the outside numbers, and it might even help that I know that this is 0. The outside number for the Y is 40. The outside number for the V is 90. The outside number for the W is between the 130 and the 140, and it actually looks like it's on that middle line, so that would be 135. And then the Z is on 180. So what I can do by doing this is whenever I'm looking for an angle, I could find the difference between the 2 numbers that represent the 2 sides, and then I'll know what to measure the angle. So Y is here, OW. So we're looking between 135 and 40. So if I do 135 minus 40, I get 95 degrees. For XOY, we have XOY between 40 and 0 is 40 degrees. We should never have a negative angle, so if when you subtract you get negative, just flip it. VOW is 135 and 90, so if I subtract those, I get 45 degrees. WOZ, so WOZ, 135 and 180 is a difference of 45 degrees. And then YOZ, between 180 and 40 is 140 degrees. So what we found is we do have one pair of congruent angles, right? Both of these, parts C and D, are 45 degrees. So I'm going to mark VOW with one curve, and then WOZ is going to have a matching curve. And that's how I'm marking that they're congruent. So the next thing is called the Angle Addition Postulate, and it's really important to know this because we're going to use it a lot in Chapter 2 and onward. So the Angle Addition Postulate says that if point P is inside or in the interior of angle RST, then the measures of the 2 different angles it forms add to the total angle. So the measure of angle RSP plus the measure of angle PST add up to the entire measure of angle RST. So it's sort of common sense, right? It makes sense that this one plus this one is going to equal this one, but now we have a name for creating this equation. It's the Angle Addition Postulate. So here we're getting a little bit of the angle addition postulate and a little bit of the word bisects all at once. So we have ray SA bisects angle RST. So I'm going to start by drawing angle RST. And it doesn't matter how I draw it, how big I draw it, it's not drawn to scale. So that's R up here, S is at the vertex, and then T. And SA bisects it. So exactly in the middle, or the best we can get it, we're going to have point A. And then it also tells us B is in the interior of angle AST. So angle AST is here. There's going to be another one somewhere in here, point B. And they're telling me angle ASB is 11 degrees. So I'm going to give a different color here. ASB is 11 degrees. And remember, this angle is the same as this angle. I want to go there first. BST is 25 degrees. So what we're looking for is the measure in the entire angle. So if we take this one piece at a time, I know this is 11, I know this is 25. So together, angle AST, I'm going to use it on the outside just so it's easier to see, is 36 degrees, right? If I add 25 and 11, I get 36 degrees. And because they told me this information, the fact that SA bisects RST, and I knew then that this piece was the same as this piece, this is another 36 degrees here, because it has to be the same as AST. So if I'm looking for the measure of angle RST, that's the 36 that's here, and the combined 36 that's here. So together, we get 72 degrees for the measure of angle RST. All right, so you're going to go ahead and try this one and answer it in the program. The last problem we're going to talk about, we are looking at perpendicular. Remember, perpendicular means it intersects to form a right angle. So they're telling me KO, which is here, is perpendicular to HM. So this angle is a right angle. So that tells me 3y plus 6 equals 90. Right angles are 90 degrees. So I'm going to subtract 6. I get 3y is 84. And I'm going to divide both sides by 3. And I get y is 28. All right. Then it stands to reason that if this is a right angle, so is every single intersection here, including this one. Now what this tells me is that together, using the angle addition postulate, these add to 90. So that's what I'm going to do. I'm going to do 9x plus 3x plus 6 equals 90. So we have 12x plus 6, I'm going to subtract that 6 right now, equals 84, and x equals 7. All right, and that is day 1 of chapter 1.